Namaskara. We were looking at the various case studies to understand the way in which the algorithmic thinking can be done in divide and conquer paradigm. Some of the historically important and significant algorithms are based on the divide and conquer paradigm. We have seen already about merge sort, and then we have looked at various ways in which we can solve efficiently the problem of finding the maximum and minimum, and we started our discussions on the Karastuba's algorithm for multiplying two n-bit numbers. So, we will continue our discussion on Karastuba algorithm. You are given two n-bit numbers, A is A1, A2, etc. AN, and B is B1, B2, etc. Bn. The naive way involves n square bit multiplications and this naive method is also known as a high school method. In the school we simply multiply digit by digit, same here bit by bit. When you multiply you require n square bit multiplications. Here is the divide and conquer algorithm. Split A into two parts, write A as A1 times 2 power n by 2 plus A2. Therefore, A1 will be A1 to an by 2, and this will be your A1. Similarly, an by 2 plus 1 to an, this will be your A2. The least significant bits, n by 2 least significant bits and n by 2 most significant bits. So, you can write A as A1 times 2 power n by 2 plus A2, and similarly you can write B as B1 2 power n by 2 plus B2. Therefore, AB is A1 2 power n by 2 plus A2 times B1 2 power n by 2 plus B2, and that is given by A1 B1 A1 B1 power 2 power n plus A1 B2 plus A2 B1 2 power n by 2 plus A2 B2. So, you can see that if I want to compute AB, I have to compute three quantities: the coefficient of 2 power n, the constant multiplying 2 power n by 2, and the constant term. Okay. So, we will write the quantities we want to compute as in the following way. So, x1 is A1 B1, x2 is a1 b2 plus a2 b1, x3 is a2 b2. If I compute these quantities, then I can find out AB by multiplying x1 with 2 power n, x2 with 2 power n by 2, and x3 I will consider as it is and add all of them. So that requires only addition of 2 n bit numbers maximum, right. So this involves, the naive way of doing this is computing a1 b1, a1 b2, they cannot be recursively done because they are n by 2 bit numbers. This involves performing 4 n by 2 bit number multiplication, namely m1 is a1 b1, m2 is a1 b2, m3 is a2 b1, m4 is a2 b2. These 4 multiplications are multiplication of 2 n by 2 bit numbers. All these things are multiplication of 2 n by 2 bit numbers. Therefore, if Tn denotes the number of bit operations if Tn denotes the number of bit operations done to multiply 2 n bit numbers, so you see that I am writing bit operation. That is because bit multiplication, bit addition, all of them they are going to take order one time. They are all constant operation. Multiplying 2 bits, adding 2 bits, all of them are adding one operation. Therefore, the total bit operation, total number of bit operations. So I consider multiplication, addition, all the count. So let Tn denote the number of bit operations done. Then Tn is given by 4 Tn by 2, because these 4 multiplications are multiplication of n by 2 bit numbers. Therefore, I have to do that, and after multiplying I have to add m2 and m3 to get x2. What is x2? x2 is m2 plus m3. These are 2 n bit numbers, right. So a1 b2, a2 b1 is, m1 is as such x1 and m4 is as it is x3. Therefore, this is the addition you have to do, and after that you have to multiply x1 with 2 power n, x2 with 2 power n by 2, and then add. Okay. So that requires another certain number of bit additions. So we can calculate exactly the bit additions involved in this. For example, if you want to, so plus, it is order n, we can even work out exactly how many it is. It is not a. So, here 2 power n means it is a shift operation. You are multiplying by 2, okay, just a shift operation. So, that is going to take n bit operations, and this one is another n bit operations, another n by 2 to multiply by 2 power n by 2, okay, adding all of them, another 2n plus n plus n, all put together around 6 and 2, 8n. That is all you are going to get maximum. So, this is going to be order n bit operations, and this by our master theorem is order n power log 4 to the base 2, which is order n square. So, this is the direct divide and conquer algorithm, and this has the complexity order n square. Now, what Karastuba has done is the following. He found out that you do not have to compute M2 and M3, okay. There is a way to avoid those two multiplication, and we can get the job done with a little more addition operation, okay. So, what he has done is he has calculated M1 as A1 B1, but M2 as A1 plus A2 times B1 plus B2, and M3 as A2 B2. So, this is directly X, okay. This is directly, what are the three quantities we were, x1, x2, x3, okay. One is directly x1, this is directly x1, and this is directly x3. However, I am going to compute x2 as M2 minus M1 minus M3. So, you can see that M2 is equal to A1 B1 plus A1 B2 plus A2 B1 plus A2 B2. So, when you are considering M2 minus M1 minus M3, so you subtract from this minus A1 B1 minus A2 B2, and that cancels these terms, and that gets you A1 B2 plus A2 B1, and that is nothing but your x2. Therefore, x2 can be computed from M1, M2 and M3. Some additional bit operations are done, namely you have to do this many additional bit operation, right. From one n bit number you have to subtract another n bit number and again another n bit number, that is okay, all of them can be done in order n time, but then you are doing only 3 multiplications. Therefore, you see that this is T of n is 3 times T of n by 2 plus order n. T of n is given by this, and the solution for this is given by n power log 3 to the base 2, which is nothing but order n power 1.56 kind of a number. So, this is significantly faster than O n square. What was considered as something impossible, through divide and conquer technique, a more efficient solution has been obtained. This is a breakthrough kind of a result. It surprised the entire world that wow. So, you can do multiplication of 2 n-bit numbers in less than n square time itself is a surprising result. So, what we are going to do is a bit more, we will take this opportunity to dig little deeper into certain technicalities related to this. Okay. So, if you look at the multiplication M2, M2 is multiplying A1 plus A2 times B1 plus B2, this is M2. But this can be n by 2 plus 1 bit numbers, because A1 and A2 may be n by 2 bit numbers, but A1 plus A2 may be n by 2 plus 1 bit number when you add to n by 2 bit number. Similarly, this may also be an n by 2 plus 1 bit number. So, in reality we have equation of the type T of n is less than or equal to 3 times T of n by 2 plus 1, because these are n by 2 plus 1, right? Plus of course order n there is no change, but here you may have something like this, a slightly larger value by a constant. Okay. So, this does not fall into the category of master theorem. You cannot apply any master theorem, you cannot use any of the standard results to get a bound on this kind of recurrences. Okay. So, we need a special trick. How do we deal with this? So, if you look at the master theorem, we have used a special infinite series. For example, for merge sort we have used the powers of 2, okay, and for the master theorem of T of n equals A times T of n by B plus order n power d, we use n of the form b power k. When it is n by 2 we use 2 power k, powers of 2. Otherwise we use b power k and then we try to simplify, expand and simplify. Okay. So, the way in which we would expand and simplify, we can apply the same technique, except that we have to come up with a slightly different infinite sequence which has the pattern. So, what is the pattern that we have used here? So, if you look at T of n equals A times T of n by B plus n power d, by assuming n is a power of b, you get T of b power k is A times T of n by b is b power k minus 1 plus n is b power k whole power d. So, you see that d of b power k is expressed in terms of b power k and b power k minus 1. So, I can now substitute b power k minus 1. This implies T of b power k minus 1 is nothing but A times T of b power k minus 2 plus b power k minus 1 whole power d, and I can plug in this value here. So, when I plug in this value I get T of b power k is A times a times t of b power k minus 2 plus b power k minus 1 power d and the other term b power k whole power d. This is nothing but a square t of b power k minus 2 plus a times b power k minus 1 power d plus b power k whole power d. So, now you see the pattern emerging. Now I have to replace this because I have t of b power k minus 2, I can use this and replace k by k minus 2 and so on, and this can go on up to k stages, and finally you get t of 1 which is a constant and then an arithmetic or geometric series. So, the algebra related to that was done, and that is how the master theorem is solved. So, what is important here is I require a pattern something like this. So, I have to consider an infinite series in which this pattern can be embedded and then I can use it. So, let us consider this question specifically. T of n equal to 3 times 3 of n by 2 plus 1 plus order n. Let us simply write as n. Some constant is there, that is not necessary, just to avoid the clutter. If you consider n is of the form 2 power k plus 2, then what can you say about n by 2 plus 1? Then n by 2 plus 1 is 2 power k minus 1 plus 1, this is n by 2 plus 1, and that is equal to 2 power k minus 1 plus 2. So, you can see that t of, therefore, I can write like this, t of 2 power k plus 2 equal to 3 times t of 2 power k minus 1 plus 2 plus whatever is that value, 2 power n is 2 power k plus 2. So, now you see the interesting pattern. Whatever is on the left hand side, when k is replaced by k plus k minus 1, you see it in the recursion. So, I can write from this you can write t of 2 power k minus 1 plus 2 is 3 times t of 2 power k minus 2 plus 2 plus 2 power k minus 1 plus 2. So, now you can plug in this value here, right, you can plug in this value there. So, when you do that, you get the following: t of 2 power k plus 2 equals 3 times t of 2 power k minus 2 plus 2 plus 2 power k minus 1 plus 2 plus 2 power k plus 2. This is nothing but 3 square t of 2 power k minus 2 plus 2 plus 3 times 2 power k minus 1 plus 2 plus 2 power k plus 2. So, we will write one more term just to figure out a pattern, and then we can write inductively the term that we will obtain in the kth stage. If you go further down k further steps, what we would get we can write inductively by looking into the pattern. Let us fit t of what is t of 2 power k minus 2, t of is 3 times t of 2 power k minus 3 plus 2 plus 2 power k minus 2 plus 2. This is the value. This value we substitute over here. Therefore, t of 2 power k plus 2 is 3 square times 3 times t of 2 power k minus 3 plus 2 plus 2 power k minus 2 plus 2 and the other two terms plus 3 times these terms. You copy down here, and this is nothing but 3q t of 2 power k minus 3 plus 2 plus 3 square times 2 power k minus 2 plus 2 plus 3 times 2 power k minus 1 plus 2 plus 2 power k plus 2. So, the pattern is very clear. In the kth term, if you go down, you will get 3 power k t of 2 power k minus k plus 2 plus, when you have 3 power k as the first term, the next term will be 3 power k minus 1 and they add up to k. You can see the powers of 3 and powers of 2, they add up to k. Therefore, it will be 2 power 1 plus 2 plus 3 power k minus 2 times 2 square plus 2. So, in this way we will have powers of 3 will reduce and powers of 2 will increase. When power of 3 becomes 0, power of 2 will become k, and that is the last term here. The last term here is 2 power k plus 2 because 3 power has become 0. So, I can write, and this is t of 3. So, this is equal to, I write like this, 3 power k times t of 3 plus, here I have 3 power k minus 1 times 2 plus 3 power k minus 2 times 2 square plus 3 power k minus 3 times 2 cube. Okay. And finally, I have 3 power 1 times 2 power k minus 1 plus 2 power k plus 2 plus, this is the powers, then 3 power k minus 1 times 2 plus 3 power k minus 2 times 2, this terms, the 2 which is in every term, 2 in every term, plus 3 power k minus 3 times 2 plus 3 power 1, finally you are 3 power 1 times 2. So, we have several terms, we can add, we can compute each one of them, all right. So, for example, what can you say about this term? This is simple. It is 2 times 3 plus, you can take even 3 for instance, 2 times 3 times 1 plus 3 square up to 3 power k minus 2, which is 2 times 3 times 3 power k minus 1 divided by 3 minus 1, geometric sum series. Okay. Therefore, this is a 2 gets cancelled, this is 3 times, therefore, this is nothing but 3 power k minus 3. So, I have 3 power k minus 3 for this part. And what about the other part? Okay. So, let us look at that. So, here we have further three power k minus 1 times 2 plus 3 power k minus 2 times 2 square plus 3 power 1 times 2 power k minus 1. You take 3 power k outside, this is equal to 3 power k times 2 by 3 plus 2 square by 3 square and all the way 2 power k minus 1 by 3 power k minus 1. Again you can take 2 by 3 and you can write like this, 3 power k times 2 by 3 times 1 plus 2 by 3 plus 2 square by 3 square. Okay. Even in this infinite series, even the infinite series if you take, it is a geometric progression with common ratio less than 1. Okay. This infinite series which is less than 3 power k times 2 by 3 times 1 by 1 minus r, 1 by 1 minus 2 by 3. This is the sum of the infinite series. This is only finite. Even if you take the infinite series, this is the value you get, and this is 1 by 1 over 3. Therefore, 3 goes to the top, cancels with the 3 in the denominator. Therefore, this will be 2 times 3 power k. So, this term is less than 2 times 3 power k. So, I have several, this term is less than 3 power k, this term is actually equal to 3 power k minus 3. So, you can say it is less than 3 power k. So, this term is less than 3 power k and this term is less than 2 times 3 power k. So, all of them put together is less than 3 times 3 power k. Okay. And T of 3, what is T of 3? Multiplying two 3-bit numbers. Multiplying two 3-bit numbers, even if you do naive way, 9 multiplications, right, maximum 9. Let us take 9. Therefore, assuming T of 3 is 9, assuming T of 3 is 9, because directly if you want to multiply two 3-bit numbers, assume you have done in a naive way, even then it is only 9. Therefore, T of n which is equal to T of 2 power k plus 2, T of 2 power k plus 2 is less than or equal to 3 power k times 9 plus 2 times 3 power k plus 3 power k minus 3, but anyway I am dropping that 3. So you see that it is about 12. So it is less than or equal to 12 times 3 power k. So how do you relate n and k? So when you try to relate n and k, here you see that n equal to 2 power k plus 2. Therefore, floor log n equal to k, and if you take n equal to n equal to 2 power k means 2 power k is less than n because n is more than that, and it is less than 2 power k plus 1. Next power of 2 is way larger. So when you take log, you get k less than log n less than k plus 1. It's less than k plus 1. Therefore, you clearly see this is less than, k is less than log n. Therefore, this is less than or equal to, since k is less than log n, is less than or equal to 12 3 log n to the base 2, okay, T of n I am expressing as a function of n. But what can you say about this? A power log b to the base c is same as b power log a to the base c. I can exchange this a and b. You can see that I can exchange it. This is a basic property of log. One of the basic property of the log function is a power log b to the base c is same as b power log a to the base c. Therefore, this I can write as 12 n power log 3 to the base 2. So 3 and n are exchanged. This is nothing but order n power log 3 to the base 2. The same conclusion we get, but with a slightly different algebra. We are considering a different infinite series. We are considering a different infinite series. Of course, we then use the monotonicity and extend for all n. Okay? All those things can be done. That is a usual thing. The crucial point is choosing the right infinite series to get to the pattern, expand and simplify, and so on. Therefore, if you are wondering whether this is true, you can see that by checking. For example, y a power log b to the base c is same as b power log a to the base c. Why is this? You take log to the base c on both sides, you see that left hand side you get log b to the base c times log a to the base c, and that will be equal to obviously log a to the base c times log b to the base c. So taking log to the base c, from this you get this, and this is obvious. Therefore, we can exchange a and b. That is the reason why 3 power log n to the base 2 is same as n power log 3 to the base 2, and this completes our analysis. Okay? And quickly we will see how this can be extended for something which is general. For example, if I have T of n equals a times T of n by b plus c plus n power d, some whatever it is. But here you have n by b plus c. What we had was n by 2 plus 1. But in general, if I have n by b plus some other constant, what infinite series would work for us? Okay? And okay, we will continue our discussions in our next session. We will briefly extend this, we will conclude the discussion related to that in our next session. Okay, thank you.